member here in the University of Washington in the Department of CS. And so Carlos, I guess you're one of the people I don't actually need to read the paper about. So I actually know all of this stuff. So Carlos got his PhD at Stanford and did great things there. And he went on to CMU where he was a professor. And I became aware of Carlos's work because he was one of the first people to realize the importance of submodular functions in machine learning, and then went on to do a number of fantastic things in that area. And then also, if that wasn't enough, of course, he started working on parallelism in machine learning and has done a lot of great things there. And that's, of course, a very critical problem that we all have right now, which is that computers aren't fast enough, and machine learning is, people who do machine learning want to do new things, and of course parallelism is the one way that to make things faster. So anyway, that's what the talk is going to be about today. Carlos, of course, is here now, so this is great. Yeah. So I'll start out.
Go ahead. I'd like to add that Jeff is really the person who has seen some modularity as important in machine learning, so it's just being too kind to me. It's very exciting to be here. We can make this talk interactive. I thought I'd talk about some context, some concepts around large-scale computation and how they fit in with respect to machine learning. And the inspiring project for us has been this GraphLab project for large-scale machine learning that we've been working on for a few years now. And my student Yu-Cheng Lo, who's one of the leaders, is just moved to UW. And so feel free to bug him, interact with him, talk to him, make him feel welcome. That's very, very nice. The other members of the group here are Joey Gonzalez, Abu Firullah, and Jay Gu, and then my postdoc, Danny Dixon. And the idea of big data has been around for a little bit now, and data just keeps growing very quickly in very interesting ways. But I think this article from the New York Times a few months ago really summarized it. Data these days is seen like an economic asset, like currency or gold for companies, which is pretty cool. But that asset is not really going to be viable or really come to life unless you do something with that data. And I think machine learning, or being able to design algorithms that scale up and tackle that data and extract some value from it, is something that is super exciting. And we have to do this in the context of these new computer architectures, in the context of the GPUs, computer clusters, the cloud, multi-core, and so on. And doing that is hard for people like us. We end up trying to solve problems that we don't really understand, problems around parallel computing, where machine learning experts, or really, Yu-Cheng, Joey, my students, end up trying to deal with things like race conditions, distributed states, race conditions, communications, and we really don't care about the states. And we end up developing code that nobody can use, nobody can maintain, nobody can debug. And because of that, there's been a push in the last few years to use large-scale abstractions or high-level abstractions to program machine learning algorithms. So today I'll talk a little bit more about these abstractions than specific algorithms. There'll be a couple of algorithms that I'll mention. But as you think about the type of techniques that you might be doing in AI or machine learning, you should be thinking about how can these abstractions support me, how can they help me scale up to very large problems. So one that's been quite popular in the last four or so years is MapReduce. This is an abstraction which is very good for data parallel tasks. So let's say I have a ton of images from Flickr, and I want to extract faces from each image. So I can just independently feed an image to a particular CPU and do some computation, extract some features, and do some local classification. So this approach is good when the problem is easily broken into independent subproblems. And the question that we ask is, when is this useful? When is this enough? And for things like extracting features in images, doing cross-validation, computing sufficient statistics, that kind of MapReduce architecture is quite good. But one fundamental question is whether there is more to machine learning. Are there problems in machine learning that don't fit into this abstraction so well? So what I'll talk today is a little bit about the types of problems that don't fit in, and what kinds of things you might learn or be able to do, and how you can fit your own solutions to large-scale problems here. But let's start with a problem that's pretty simple. Let's say I'm trying to do regression. So I'm trying to fit some function to data, for example, this polynomial degree 3 to these points. And the idea here is that there's some target function y that I'm interested in is a set of basis functions, let's say polynomials, and I want to estimate the set of weights W. And one thing that's been quite popular over the last few years is to try to do this in a sparse way. To try to find a set of parameters W that's kind of minimal or sufficient to fit this entire function. And this is typically done, or often done, using the sparse methods, for example, lasso, where you have a standard regression problem. So I'm trying to fit this function with least squares, and I have an extra penalty. Hello. And I have an extra penalty that pushes me towards a sparse solution. This is this L1 regularization penalty. And this is just a simple example I'm going to introduce in the beginning. We're not going to dive into too much, but it provides some intuition as to what might be easy to parallelize or might be hard. So let's say that I want to solve this problem, which has been useful in computational biology, computer vision, and computer science, and any other tasks. One of the most successful approaches for problems with very large feature spaces, which was called coordinate descent. And the idea is quite simple. Let's say there is a function I'm trying to minimize. I'm trying to get to the bullseye here. I start from some point, I pick a coordinate, let's say the x-axis, and I go to the minimum of that coordinate. I pick another coordinate, let's say the y-axis, I go to the minimum of that, and proved by PowerPoint, we get to the optimal solution. And one question you might want to ask is, can somebody be the designated? You can.
I can't do that.
Oh,
Get the alarm.
no bias.
Yeah.
He's blind, so you have to open it.
So coordinate descent is one solution method. And the question is, how can you parallelize this? And one approach that we developed recently, my students Apo Kirula and Joseph Bradley did, is to develop, so this algorithm here is called the shooting algorithm because you pick a coordinate and you shoot along that coordinate. So they asked the question, what if we created what we call a shotgun algorithm, where you put multiple coordinates and independently you optimize them. So let's say the x-axis and the y-axis in this picture, and again, proof by PowerPoint, you get to the optimum in one step, in parallel. The problem is that this picture is extremely misleading. For example, if your function is not that little bullseye, but it has correlated features, so unlike this nice circular uncorrelated case, you have some correlated features. What ends up happening is, if I try to optimize the x-axis, I'm going to go all the way over here. Optimize the y-axis, go all the way over here. And you can end up in a point that is worse than where you started. So breaking a problem into independent subproblems might not be a good solution to this task. So the question that they asked was, is coordinate descent inherently a sequential problem? Can it only be solved in a sequential way, or can you parallelize it in some way like this? And this is the kind of only theoretical result I'll talk about today. But the result basically says, and this was the beautiful insight that Joseph and Apple had, it says that you can achieve what are called linear speedups or improvement in performance in terms of number of processors if you don't have that many processors compared to the number of features in the problem. So in particular, if you have p processors, and these are dimensionality of the problem, and rho is the largest eigenvalue of a particular matrix, then if you have at most d over rho processors, then you can achieve linear speedups, you can achieve nice conversions. So in particular, if the problem is totally independent, then this rho is equal to 1, and you can have d possible processors for d dimensions. That means that you can get the optimal case, beautiful, everything is independent. In a highly correlated case, in the worst case, rho will approach d, and you can use at most one processor. So this theoretical analysis of the problem says sometimes it's possible to solve it in terms of independence of problems that get iterated, and sometimes when the problem has certain characteristics, it's not. And the beautiful thing here is that if you look at increasing the number of processors and the rate of convergence, you see that the theory really behaves quite nicely in practice. You get linear speedups, linear speedups, linear speedups, until you hit kind of the predicted level of the theorem, and it starts to behave in a not so nice way.
So you are still doing
a different processor on a different dimension, or does the algorithm intelligently chooses the subset of dimensions on which to do
You just pick one at random and then you execute it.
Is that theoretical result true for all forms of regularization or all orders of regularization?
It's true for, it was mainly focused on L1 regularization, but it's true for a wide range of decomposable loss functions. So logistic regression and some other loss that you might have in mind. Any other questions here? So Shotgun was a nice example. You know, it provided nice speedups. It compared to a bunch of things. It did really nicely. It outperformed state-of-the-art systems. But I think it's an example more like broader picture of the stock. Is where you took a problem that wasn't particularly easy to parallelize, or wasn't particularly data parallel, and you prove some theorem that allows you to solve it with something like MapReduce. And so at some point, for some algorithms, you might be able to do this. Like you might be able to take the problem, it's not exactly feature selection or something, but you can still solve it in this data parallel fashion. But the question, the more fundamental question today, and I think the more fundamental question as we push machine learning further to these large scale problems, is when is this cycle not possible? When is it not possible to just go and transform something that can be solved in independent ways? And when do you need new kinds of abstractions that MapReduce is not sufficient for? So what I'll do is I'll show you a bunch of kind of pictorial views or kind of illustrations on the type of questions where this is not good. So here's one question. What is this? It's hard to tell. I think Ira should be able to tell me, and I'll tell you why in a second. It's near this. Does that help? But if I show you the whole context, then you get a better sense of what each thing is. So, and you have to be able to do it. You work in computer vision, and so you must be able to solve all problems. Looking at the independent patches of an image is not sufficient when you're trying to kind of understand the context of things or do recognition. And this is true for a wide range of problems in machine learning today, computer vision, AI, and so on. I think that the dependencies in the data is where it's important. So I'm going to show you a couple, again, toy examples. Let's say that I take this picture and I label it. It's my grandma. And I have this other picture, and I ask, who's that person in the middle? Somehow these images are not similar enough to figure out that that's the same person. But I might have other data. For example, there are other images where there are similar faces that maybe can be related to the image in question. And there are other people that appear in the same image, and people appear in co-occurring, gives me some information about who that person might be. So somehow if I can propagate this information through some model or some other structure that exploits these dependencies, I can make better predictions as to who I see in this image. So this is an example where the dependencies in the data are very fundamental. Here's another example that's very well known, collaborative filtering. Let's say that you have a particular user that liked Lord of the Rings, for some reason does not like Star Wars 4, but likes Star Wars 1. Also like Harry Potter, and you say, okay, what else should you recommend to this person? Maybe this person is pretty easy to say. Maybe you'll say Pirates of the Caribbean or something. But let's say that you take somebody who's slightly more idiosyncratic and say, liked Women on the Verge of a Nervous Breakdown, great movie, The Celebration, City of God, and Wild Strawberries. What else should I recommend to this person? So that might be a little more complicated, but you know.
Star Wars 1.
Star Wars. Exactly, yeah. But there might be some other person around who's a perfect match for this person, who seen similar movies, who like the same, and who also like La Dolce Vita, and maybe this is a good recommendation. So thinking about collaborative filtering problems where you have, again, graph dependencies in the data. Maybe people watch movies and rated them, and some kind of propagation algorithm in this graph allows us to make better predictions. Another example that we'll talk about today, and I'll show you some results for, is LDA. So let's say that I have a bunch of documents that are associated with words. So these are the words that appear in each document. You can imagine forming by graph here. And you want to discover topics or related topics associated with each document and each word. And in your head, maybe there's a topic about cats, very important. There's one about computers, one about Apple, and so on. And by doing some kind of propagation and analysis of this graph of dependencies, you can come up with topic models that may be discovered from data that capture things like cars and wars and arts and so on. So the idea or the problems, I think, where things like MapReduce don't work so well are things where you start from data, that might be image, documents, movies, and so on. You might do some initial feature extraction, but there's some graph that's formed, and there's some structured machine learning algorithm that exploits the dependencies in this graph. And for the first part of this problem, which I'm going to call graph ingress, or this graph formation problem, data parallel abstractions like MapReduce tend to be quite good. But for problems that involve dependencies, you think you need some kind of graph computation type structure, and this is where we're going to need new things. And so today I'll talk a little bit about abstractions that allow you to focus on the purple box. So if things like feature extraction feel well in the MapReduce setting, on the right side you might have things like graphical models, semi-supervised learning, collaborative filtering, graph analysis, and other things. So that's the focus of the types of abstractions we're going to talk to today that might be useful in your research. So as a running example, I'm going to use a very simple graph parallel, very simple example of graph parallelism. This is just a random walk on a graph or a page rank. So the idea is you have a social network. I want to make some prediction about the rank of a user. And I don't know anything about the user, but I say, oh, the rank of the user depends on the rank of the people who follow this user. And then what is the rank of those people? Well, it depends on the rank of the people who follow them. And since this graph has loops, you iterate some algorithm on this graph. You iterate some updates in order to make some predictions about everybody's rank. And the type of updates that you do is just to say, iterate until convergence. My rank is the weighted average of my neighbor's ranks, my friend's rank. And there's an equation here to cite for those who care. So I want to iterate, my rank is the weighted average of my friend's rank, and that's my algorithm. So I have some graphical dependency in data. I want to do a local update. My rank is the weighted average of my neighbor's rank, and I want to iterate that again and again and again until convergence. And this is the kind of problem that I think many of us want to solve, and this is the kind of problem where MapReduce is not so appropriate, and you need what are called graph parallel abstractions. And when you start thinking about those, you have to start thinking about new concepts in distributed systems, and I wanted to introduce one of those here so that you guys are familiar with that, because I think it really informs the design of machine learning algorithms. And it's the idea of synchronous algorithms versus asynchronous algorithms. So a synchronous algorithm, and an example of a system supports that is the Pregel system, which is really an abstraction due to Valiant in the 90s. And it's very simple. Synchronous algorithm will take a graph, and it will associate some computation with each vertex in the graph. And it will say, do some computation, and after you're done with that, send some messages among neighbors in this graph. When you're done with that, you iterate. So these types of algorithms are pretty common. For those familiar with linear algebra, these are called Jacobi updates. And the issue, though, is that for machine learning tasks, these types of algorithms tend to be quite inefficient. In fact, you can prove some nice theorems, again, that I won't get into detail, that show that you can do very badly. And instead of going to details of that, let me show you a picture of what you expect. So here's a graph of dependencies in data. let's say graphical model or some other graph structure they might be interested in, and you want to make some prediction in this graph, but there is embedded in this graph a set of very strong dependencies that you don't know about, but only after the data gets propagated along this subgraph do you make good predictions about this vertex over here. And if this is the situation that you have, then you have to focus computations in these parts of the graph more often than the rest. And the only way to do that is by doing some kind of prioritization of the computation as you go, because you don't know where you should go. And doing bulk synchronous updates is wasteful because you're spending time up here when it's quite unnecessary. I can do a simple illustration of that. Let's say that you take this very toy image denoising problem. So I have an image, we added some Gaussian noise, and I'm trying to remove that noise by putting a graphical model that connects neighboring pixels in the image. And if you look at it, you'll see that the more complex or more challenging part of the problem is in these boundaries. It's in the regions where the image is changing colors. This is where your computation should go. If you use an asynchronous algorithm, what you can do and what it will do is in the beginning, it will run updates everywhere, and then realize that there are some regions of the graph that are more challenging, and you need to spend more time on those regions. And your updates end up focusing on this part of the graph much more often than on the rest. So if you're able to design algorithms that exploit this property, you can get much faster conversions. And so here's an example. I'm increasing the number of processors, and I'm looking at the running time to reach a certain convergence level. If you use the standard synchronous algorithms, you get this kind of convergence rate, which if you didn't care about it, you'd be very happy, because the speed ups are very good. You had one processor, you had this running time, you have 8 processors, you have basically 8 times faster. So you feel very good about yourself. But the problem is that if you compare this with the asynchronous algorithm, you get much faster conversions. In fact, an asynchronous algorithm with 1 processor is faster than a synchronous algorithm with 8 processors. And again, this is a theorem about BP, about belief propagation, for those familiar with it, that says that asynchronous algorithms can asymptotically be significantly faster than synchronous ones. So a few years ago when we had these papers, we were feeling pretty good about ourselves. We had some nice theoretical results. We were feeling, like we're making a lot of progress. But the truth in advertisement, or the reality of it, is that implementing these parallel algorithms was really painful. We wasted a lot of time. It was really, really a big waste of time from a machine learning perspective. Yes?
I was wondering if you could go into a little more detail about the assumptions that make this difference between synchronous and asynchronous, because there must be restrictions on the synchronous model that don't allow things like, okay, everything works in this bulk synchronous way, but nodes have the ability to turn themselves off and say, I'm done, I'm too far away. I mean.
Oh yeah. You could do right. So you could do things like a weaker version of bulk synchronous, where at every step you only touch certain nodes and some kind of adaptivity. And in order, at least in this particular problem, in order to achieve this theorem, you have to have a prioritization over nodes. You can imagine an example of this is very simple. It's a wavefront type algorithm. In that case, it's not necessarily about turning off. You have this kind of wave of information that needs to be propagated. And more generally, there's some kind of priority queue over the data. But it's true that you can go from bulk synchronous to fully prioritized in various ways. And we've played a lot of this.
So it is very similar to prioritized sweeping
in a sense, prioritized sweeping is another example of a problem where if you have prioritization, you can guarantee better things about it. And it's an asynchronous algorithm, so it's a really good example of this.
So borrowing from the same literature, a lot of MDP algorithms today use a combination of prioritization and search. So they don't even touch a lot of nodes which are not even relevant for problem solving. Is there an analogous version in belief propagation that has been considered so far, or not? So I'm thinking about algorithms like LEO style or TTP, which are...
I understand what you're saying. There are these algorithms in like based on beam search, they try to solve it. It's not exactly BP, but try to solve the maximum likelihood type problems or map inference type problems. And you can view them in a similar light. But there's probably room for cross-fertilization. Any other questions? So if this is the type of algorithm that we wanted to build, and this is the type of algorithm that seems to work well for like state-of-the-art machine learning, the question was, but it was extremely painful to build it. If I wanted to go from BP to say prioritize sweeping MDPs, I would have to start from scratch. And I wouldn't be able to transfer the ideas from one domain to another. And that was kind of the genesis of the GraphLab project when I was back at CMU. And the idea was to be able to support the needs of this iterative, prioritized, asynchronous algorithms in machine learning and in other fields, and simplify away the parallel things. So for somebody like me, who maybe I know how to solve a problem in one machine, like we prioritize sweeping on this graph, the dream was to be able to say, okay, I know how to solve this problem. Somehow I'm going to feed my algorithm to GraphLab and the Amazon cloud, and I automatically get some efficient parallel predictions. And if we could do this, then it would open up the possibilities of kind of changing how we do machine learning today. And that was kind of the dream when we started. And it was really a transfer of ideas from BP into this kind of more general setting. So I won't go into a lot of details about the GraphLab system, but just give you some ideas of what is it that you should be thinking about as a machine learning person or an AI person when you think about these distributed algorithms. So let's start with the first version of GraphLab, GraphLab 1. You have a graph of dependency in data. Maybe this is a social network graph, maybe this is a graphical model, where there's information in the vertices, maybe user profiles or node potentials in a graphical model, and information in the edges, for example, similarity weights in a social network, or edge potentials in a graphical model. And you have to do some computation actually. So for example, you run what's called an update function. So I'm going to pick up a vertex, and I'm going to modify potentially the data in the neighboring edges and the neighboring vertices. So for the page rank example, I would say my neighboring edges and my neighboring vertices are my scope. I update my rank based on the weighted average of my neighbors' ranks. And if things have changed enough, under some measure of change enough, I go and schedule my neighbors. And this is the idea of dynamic computation, where you only schedule things as they're needed. Again, these update functions are run parallel, asynchronous, and they're iterated into conversions. One of the interesting systems issues that comes up, and this is just one picture of what comes up, which you wouldn't have to worry about anymore if you use GraphLab as a machine learning person, is the idea of a race condition. So if I have a graph and I'm executing these red vertices in parallel, they might modify the ranks of the neighboring vertices. And so if I start executing the blue vertex, I could have a problem, because neighboring vertices might read or write to the shared data at the same time. And this is called a race condition. And when I started the GraphLab project, some people came to me and said, oh, these machine learning problems are all statistical. Who cares about race conditions and bad data? Everything averages out and you'll be fine. And what they're telling me is, if you don't care about consistency, then you're going to have higher throughput, more updates per second. And they're correct, but the reality is that this can lead to slower conversions or even divergence of machine learning procedures. So if I take Netflix data, so I'm trying to do movie recommendations, and this is the updates as they're happening over time, and this is the training error, and I'm only using 8 cores, so this is not a lot of processors, a lot of chance of collisions or anything. If I don't guarantee consistency, this is the kind of solution that you get. It basically never converges. But if you guarantee consistent updates, you get nice, quick conversions and nice solution. So as a machine learning person, you don't care about the stuff. You just want to have it happen to you behind the scenes. And what GraphLab will do is guarantee that you have this consistent updates in a kind of user-tunable way, which you can learn about. So, yes?
So, well, is there still a point to those claims that, I mean, since these are all approximate inference algorithms or some sort of approximation of some objective anyway, maybe there are subclasses of update rules
Yeah.
that are so sensitive to the lack
Yeah,
of
so for some problems, it's sensitive to collisions. This is what Jeff's saying. Is this always the case? And the answer is no. Some problems are sensitive to this collision, some problems are not. And that's why we provide this user-tunable consistency model. So as a researcher, you could say, I'm going to come up with an algorithm that is not sensitive to collisions. I'm going to run it on GraphLab. I'm going to come up with another one which it is, and I'm going to compare the two. All you have to do is change the flag in your execution. And I think there's really interesting ideas, both in machine learning and also in the database community. They came up with some really interesting theorems recently to try to characterize when collisions are bad and collisions are not bad. And I think we as a community could do really nice things around that. But the concept here is that there's an abstraction that lets you play with that kind of stuff really easily. Any other questions? So, from your perspective, you'd have to think about the data that you have as being graph structured. These update functions that modify the data. There's some notions of scheduling and consistency that I haven't gone into too much detail, but you get to play with those too if you want. And a bunch of algorithms have been were implemented in GraphLab 1 and evaluated. So let me give you one example of this. This is so Mitchell's group was doing some name entity recognition type work, and they were using this OEM algorithm, and they tried it on, first they were using Hadoop because they couldn't scale to types of problems that they had, and they were pretty happy because at least they could solve the problem they had. But then they tried GraphLab, and as you increase the number of machines and you look at the speedups that you get, GraphLab gets pretty close to optimal speedups. And they were quite happy, and in fact here are the results that they got. When they're using Hadoop with 95 cores, it was taking them about 7.5 hours. GraphLab with 16 cores took them about 30 minutes. So this is 6 times fewer CPUs, 15 times faster. But this is a cloud-based system, and this was a multi-core system. So there was also the distributed version of GraphLab, which on 32 Amazon EC2 machines took about 80 seconds for this problem. So that's about the same number of processors as Hadoop, 0.3% of the time. And then if you're Jeff or one of your advisors, you care about money perhaps, and nice thing they can do is plot the running time of your algorithm versus how much you're willing to spend on Amazon. And you see, for example, that being 2 orders of magnitude faster than Hadoop means it's 2 orders of magnitude cheaper, which is a nice thing here. So this was about a year ago, and at this point we're feeling really good about ourselves. GraphLab seemed to be really nice. And then we felt perhaps cocky or ambitious, and we said, let's solve this big web scale problem that nobody had any reported results on, which was the web graph, and we just couldn't scale up.
Question.
Didn't work. Yes?
Could you just comment on how much tuning was required to get, like, for example, the result that you just showed? Was that sort of the default?
From my perspective, from GraphLab's,
Yeah.
so the system itself required tuning, building, and so on. But today, as a user of GraphLab, you require minimal. It's minimal work from your perspective.
But what about this consistency versus?
Oh,
trade-off?
there's like three options that you get to pick. You can try them all, or you can go. We usually go for the middle one, and it usually does okay. So there isn't a lot of parameter tuning on your side. But yeah, we had this web graph with 1.4 billion vertices and 6.7 billion edges, and our system just didn't work. It was very embarrassing. And we tried to dig in and try to understand why this wasn't happening. And we realized that this graph was called a natural graph. And natural graphs have very interesting properties. GraphLab and other graph parallel abstractions like Pregel were originally designed for very regular graphs, where you have small neighborhoods, they're easy to partition, they're very regular. Real world graphs are not like that. They have some vertices with very large neighborhoods. They have, for example, power law distributed vertices, vertex degrees, and they're very hard to partition. And so as an example, in the web graph, which has power law constant of 2, about the top 1% of the vertices are touching about 50% of the edges. And this is not just a problem with the web graph. If you think about a social network, you might have a very popular person which is connected to many other people. By the way, this is an age test. Did you laugh?
He has fans of 12.
In movie data, you might have a movie that a lot of people watch, let's say Harry Potter. In machine learning tasks, you might have something like a hyperparameter, which is connected to every variable in your model. Or in text analysis problems, you might have a word that appears in many documents. And so when you have this kind of power law distributions and very high degree vertices, you can have very problematic things happening from the distributed systems kind of set. So for example, the amount of information in around the vertex can be too large for one machine. GraphLab has to touch all the data, which can be very slow. If you use something like Pregel, you have to send messages on all those edges, which can be very slow. There's all sorts of other reasons around blocking and consistency that can make the process extremely slow. And just to dig into one example of this problem, let's say that I have a variable y that has very large degree, and I end up splitting it across 2 machines. If I do that, I'm cutting a bunch of edges. And the amount of communication that the existing systems had to do was linear in the number of edges cut. And that can be extremely problematic. In fact, in natural graphs, it is well known that there's no good cuts. Even if you could solve this NP problem very well, you wouldn't get a good solution back. And because of that, the existing systems, GraphLab 1 and Pregel, use what's called hashing cuts or random partitions. Basically, that's a lot of words to say they just assign a vertex to a random machine, and then cut the edges across that. And if you do it, you get very bad solutions. In fact, it's easy to show that in expectation, if you have p processors, p machines, 1 minus 1 over p of the edges are going to be cut. So if you have 10 machines, you're going to cut 90% of the edges. If you have 100 machines, you're going to be cutting 99% of the edges with random partitioning. And so the amount of communication and data moving that you have to do is extremely large. And so GraphLab 1 and Pregel and existing systems provided poor performance in natural graphs with high degree and led to low quality partitions. And the recent new version of GraphLab has 2 innovations. One is a new way to specify how you do computation or how you do these update functions. And another one is a new type of partitioning problem based on what's called vertex partitioning that allows you to solve larger problems and think about more interesting ways of dealing with distributed data. So I'm going to spend a few minutes on this and then show a few examples on some kind of simple problems, toy problems in machine learning, and how they could fit into this kind of abstraction. So let's start with the new update functions in GraphLab 2. What they do is split the process into 3 phases. The first phase is what we call the gather phase, where you have a commutative associative function among edges of the graph, and you just go edge by edge, and you just do in parallel a sum over the contributions of each edge. And this is a kind of a generalized sum, so it can be many things, and I'll give you a few examples of that. Once you've gathered information from your vertex, from your neighbors, you change the local information on your vertex, and then you do a scatter phase where you propagate these changes back to your neighbors. So this process has 3 phases: this gather, apply, and scatter phase. So let's talk about a few examples. First, page rank, the example from the beginning. The gather phase is just this sum in page rank, the weighted average of my neighbors. So in each edge, I return the weight of the edge times the value of my neighbors, and the merging function is just the sum. The apply function just changes my rank, and the scatter function schedules my neighbors if my value has changed or not. So this is a very simple example of this three-phase algorithm, or this three-phase abstraction. Here's another example, triangle counting. Here's a very simple computation you might want to do in a large graph like a social network. So let's try to think about, if you wanted to find a very popular person in a social network, what would you do? One way is to find somebody who is connected to many people, has very high degree. Another way is to think about the person that participates in many triangles in this graph. Somebody participates in many triangles tends to be somebody in a more tightly knit community. So it's understood it's better to advertise to somebody who participates in many triangles than somebody who has very high degree, because the information propagates faster between their friends. So one task you might want to do is count the number of triangles each person has if you're, say, Twitter and you want to advertise or Facebook. And you can compute this in a gather, apply scatter phase. In a gather phase, you're gathering neighborhood lists from your neighbors so that you can figure out if any of your neighbors share any triangles. In apply, you say your own list, and scatter, you say, I'm in that triangle if my neighbor on one side is friends with the neighbor on the other side. And you can imagine how to do this. Here's a cute little result of what happens if you look at the Twitter graph when you do this. So a popular person in Twitter graph, if you just look at the number of people following them, is, for example, Britney Spears in 2010. But a person who is part of strong communities or is part of many triangles is somebody like Stephen Colbert. So it might be better to advertise to Stephen Colbert than it is to Britney Spears. Here's another example of what you might want to do in parallel using the scatter apply scatter model. Let's say I want to do belief propagation on a graphical model. Here's a particular graph. What you'll be doing in the gather phase is accumulating the product of the incoming messages to my vertex. In the apply phase, I change my belief. And in the scatter phase, I compute the outgoing messages from my neighbors. In collaborative filtering, you can do the same thing. You can imagine a problem like I described in the beginning with people and movies. You can imagine you have a particular movie and you want to associate it with these latent categories or latent topics, and the goal is to discover them, latent categories for users and for movies. And we do that based on the ratings that a user has for particular movies. And in the gather phase, I'm not going to go into the math, but the computation is basically the product of your ratings with this particular vector over here, and it gets accumulated according to my neighbors. And the apply phase is a matrix inversion where you're basically doing regression on this product. And you iterate this over movies and vertices, users and movies and pixel versions. Okay, so let me just show a few results, and then I'm going to take a step back and talk a little bit more bigger picture, some questions in large-scale machine learning that I find interesting. So if you look at convergence rate, so lowest better versus running time, if you use Pregel, this is the kind of convergence rate you get. With GraphLab 1, you're faster. With GraphLab 2, you're even faster, and there's a way to do caching where you can get even faster performance. Now, one interesting question that comes up as you think about this new version of GraphLab, and I mentioned this in the beginning, is how you partition the graph. I said that cutting natural graphs is quite difficult when you think about edge cuts, but in GraphLab 2 you do something a little bit more interesting. When I take a vertex and I cut it across machines, and I go through these three phases, I'm going to do gather independently on each machine. I compute a contribution. These get transmitted to a single machine that does locally the apply phase, and that then gets scattered across machines. And I'm not going to go into a lot of details here, but just to give you some sense of what happens or what's interesting, if I have a very high degree vertex and it gets split across 3 machines, the type of communication they have to do is linear on the number of machines that vertex is assigned to, and this is called the Vertex Cut Problem. And percolation theory shows that it is possible to solve this problem efficiently in natural graphs, unlike the original edge cut problem. And you can get much faster performance this way. And we have some very interesting cutting algorithms, which I'm not going to talk about, with some nice theorems around it, which GraphLab implements. Yes?
2 questions. So there are a couple of models. One is dual decomposition, and another is relax, compensate, recover by Adnan Darwish, which have some similar characteristics where they partition, and the second step is to ensure that the partition vertices have similar values across different partitions. So have you looked at these, and do you see a connection?
Yeah, so the way to think about this is that these algorithms could be implemented in large scale using GraphLab, using the GraphLab abstraction. So anyway, so GraphLab is this system built on top of existing things for like Amazon AWS, and it has a bunch of infrastructure. But the way to think about it is it hides all this stuff from you, and you might want to write algorithms that go on top of it. So we have now some algorithms for clustering, some computer vision stuff, collaborative filtering, and other things. And the performance you're going to get if you write your machine learning algorithms up here can be quite a lot better than you get out of Hadoop. So if you're writing dual decomposition on top of GraphLab, you can get a lot better performance and ignore all this stuff that goes on the bottom of it. So as an example, if you take counting on the Twitter graph, the best published result for this was from last year, and they used Hadoop on about 1,500 machines, and it took them about 400 minutes. And GraphLab with 64 machines takes about 1.5 minutes. Another example here is LDA. So if you take all of Wikipedia, which has about 500 million tokens, the best existing system for doing LDA in this scale of data was a system that Alex Smollett built just for LDA, and he could process about 150 million tokens per second. And GraphLab is more general. If you write something in GraphLab and you spend 4 hours and write 200 lines of code, you can process about 110 million tokens per second. So the idea is, can you do this? Can you write your algorithm this way? Again, just a couple last examples here. With PageRank, the best published result on Hadoop took about 5 hours on this problem. Twister, which is an in-memory version of Hadoop, which is faster, took about an hour, and GraphLab takes about 8 minutes. And it's a lot cheaper. And finally, let's go back to that big, large-scale web graph that we described in the beginning. I said there were no published results for it. It's hard to compare to anything else, but it had 1.4 billion web pages and 6 billion edges, 6 billion links. We used 64 Amazon machines, which is about 1,000 cores and 4 terabytes of RAM. And with GraphLab, we're able to run PageRank on this in about 11 minutes. So that's about 1 billion links processed per second and only 30 lines of code. So as a machine learning person, you'd be writing 30 lines of code and be able to use all this other stuff automatically. And just a little bit of extra advertising here for a related project. My student, so before I jump there, my student Apple Kirilla came to me about a year ago and said, buy me a Mac Mini. And I thought he wanted to watch TV. But he said he wanted to solve web scale problems on a Mac Mini. And I didn't think that was possible, but he did something quite beautiful and quite impressive. So GraphLab is named GraphLab because a lot of these cloud systems have animal mascots, and ours was a Labrador because they had a lab, so it's GraphLab. And so Apple wanted to build a small version of that, so we call it GraphChi for Graph Chihuahua. And he's able to exploit solid-state drives and hard drives to solve very large problems on the Mac Mini. So he has a very nice data structure and ideas that I'm not going to get into detail here, but just give you one advertisement result. If you take the problem that in Hadoop took about 1,000 machines for 100 minutes, in GraphLab there are 64 machines of commuters in Manhattan. Apple can take a Mac Mini and solve this problem in 59 minutes. It's pretty impressive. So in the last few minutes, I just wanted to step back and talk about where next. You know, I'm new here at UW. I'm excited to meet a lot of people and engage with students and other faculty. And I just thought I'll talk a little bit about a few of the problems that I'm very interested in. The first one is what I've been hinting at for a while, which is distributed machine learning. It's clear that the size of data that we want to deal with just keeps growing, and in comparison, the size of the machine learning hammers just keep decreasing. And so I think, you know, designing new parallel large-scale machine learning algorithms for whatever task you see out there is pretty open. There's a few solutions for specific problems, but there's real opportunity here. And it's really hard to build and implement these things. But what we talked about today, GraphLab, is a way to, after you design your algorithm, implement it easily in a large-scale setting. Another question that I'm very excited about is the fact that GraphLab and other distributed systems today are basically for batch computation. You're giving some data, you hand it to GraphLab, and you get some predictions. But that's not how the world works. Really, graphs are changing over time. So if you think about Facebook, new users are arriving, so nodes are being added. Friends are being made, so edges are being added. People are befriending people. Thanks, Jeff. So edges are lost. And so you can think about data streaming into some online system and queries streaming at the same time, and you want to make online predictions. And with GraphG, we have a first version of an online version of GraphLab, but on a single machine, but it's very hard to do this in the cloud. So I'm very interested in that problem from a system perspective. But from a machine learning perspective, there is a very related problem that nobody really knows the answer to. So how do you do parallel online learning? Let's say that I have a learning algorithm where the data is not fixed, but the data is streaming in. And how do you solve this problem in a distributed or parallel way? There's been a few theorems on this. We have a paper, a few other people have papers. But I think nobody has a good solution to this. Nobody knows how to do it properly. It's a very beautiful and very open, very easy to state, and very open problem in machine learning space. Another issue that Dan Grossman is going to be helping us with is programmability. Right now, writing GraphLab code is a bit of a pain in the ass, I must say, and admit it. You write C++ code, you have to compile it, it's annoying. And I think there's better ways of doing higher-level programming on top of GraphLab, and there's a better ways of debugging this parallel systems. I think there's really new insights we had there, and we're working on that. And another task that I'm very excited about, and I wrote a proposal recently with Jeff here and Ben Tusker and others, is this idea that today, if you think about, for example, text processing, you start with a small number of documents, you do some kind of magical pre-processing, you run into a black box, and you get some, say, topics from LDA, and you just hope for the best. Or you look at it, and you say, okay, they look good, they don't look good. But I think we need to rethink this pipeline and make it more interactive, let's say. I want to be able to deal with many more documents. I want to have some interactive way of doing the kind of pre-processing you might want to do with data. That goes to some transparent algorithm that gives you some explanation as to why some predictions are made, or some visualization of that users can interact with in a kind of active learning setting and revisit how the pre-processing or how the algorithm itself works. And closing the loop in these problems in very large scale, I think, is a very interesting and open problem. And so if you're interested in any of these problems or others, I'll be very happy to talk to you. And the final bit of advertising is that we have 2 new courses that we're developing. One on machine learning for big data, and then one that Andy is doing, Andy Fox, sitting there, on statistics for big data. And this will provide the computational, algorithmics, and statistical foundations for large-scale machine learning. Our first authoring is going to be in winter, and since this is the first time, we're actually merging the 2 courses in one, and then next year we're going to separate them 2. So for those interested, I think this would be a fun experience. And there's more happening in terms of education around big data, and I'm open to inputs on that. And just to close up, GraphLab and GraphT are both available open source today in Apache license. We have a bunch of tutorials and some documentation and a bunch of users, and we'd love to have your feedback and contributions. Thank you. Questions? Yes.
You said at the very beginning something about logistic regression with the lasso, but then that didn't seem related to GraphLab. Is that part of GraphLab? I asked because my student told me this morning that she was trying to switch in our image analysis problem from running on SVMs, which could handle her multiple thousand features, to logistic regression with a lasso, and it couldn't handle so many features.
Okay, so the algorithm that we had in the beginning, the shotgun algorithm,
Yeah.
is one of those earlier things that we did before GraphLab was in the current state, but it's available in open source, and it does logistic regression lasso. It's a standalone system today. It hasn't been integrated
It's not
into
in-
GraphLab. But it still works in parallel and scales really well, so you might want to give it a try. Or give us some feedback and we'll try to make it better.
I'll be sending her to you.
Any other questions?
So it seems like a lot of the stuff, especially in terms of like the graph partitioning and the vertex cut stuff, would be more general than just machine learning problems. Like, for example, fluid dynamic problems are constantly used in these kinds of things. So why stop at machine learning?
Why stop at machine learning? That's a good question. I don't stop at machine learning. This is a way to draw a line in the sand in a way that if you scope it in a certain way, you can think about problems more completely. And you don't have to say whether or not you can do everything in the world, but I think it's applicable to other settings. I think the idea of vertex cuts is really beautiful and very widely applicable and still to be explored. Presenting the paper on that on Monday, so it's kind of very good stuff. Any other questions? Okay, thank you very much.